Hello everyone, welcome back to lecture series on aerospace propulsion. So, in the previous lecture, we were discussing about the operating conditions of our nozzle for conversion nozzle and conversion diversion nozzle. Okay, and what is the consequence of operating our nozzle in the off design condition? So, we have seen like one is you will have the thrust loss. Another one is we have seen like you will have the formation of a shock cell pattern. Okay. The shock cell pattern will result in higher infrared radiation, as well as you will have the broadband noise, that is shock noise will be very huge. Okay, so that's what we have discussed in the previous class. So in this today's lecture, what we are going to see is that we are going to discuss something about variable area nozzle. So before seeing this variable area nozzle, first of all, we are going to see what are the basic requirement of an exhaust nozzle. And then we are going to see what is this variable area nozzle and what is the need for this variable area nozzle. And then we are going to see at the end something called thrust reversal. What is the need for the thrust reversal? How do we achieve the thrust reversal in our jet engine aircraft and in the propeller aircraft? We are going to discuss in today's lecture. Okay. First, let us start with what are the basic requirement of an exhaust nozzle. Okay, so we know that nozzle is to produce the thrust in case of our engines. Okay, so even though it has to produce thrust, it has certain needs or requirements which it has to satisfy. Okay, the first one is that it should be matched with the other components of your engine. For example, you have a certain amount of flow comes out of your turbine. Okay, so the flow coming out of your turbine should be capable of entering in the nozzle, and it should be expanded to optimum expansion ratio. Okay, so why it has to provide optimum expansion ratio? Because we have seen if you are not operating your nozzle at a design condition, you have the loss in the thrust. Okay, and obviously next the basic requirement is that it should produce the minimum amount of losses during your off design as well as design conditions. Okay, a design condition means that is correctly expanded condition. Off design means under expanded or over expanded. Even if you are not able to operate your nozzle at the correctly expanded case, okay, the loss it should produce during these off design conditions should be as minimal as possible. Okay, and next one is the permit afterburner operation. Okay, so you know all the fighter aircraft will be fitted with the afterburner, right? So if you are having a conversion diversion nozzle, it should be capable of permitting the afterburner operation, and the same nozzle should be capable of providing the reverse thrust if it is necessary. Reverse thrust and all we are going to see in the later section. And next is the suppress jet noise and IR radiation. So mainly this is for your supersonic aircraft. Jet noise, obviously it is going to create the noise pollution if you are having too much noise. So it should produce the less amount of jet noise. Another one is the less amount of IR radiation, because most of the detective mechanism in your fighter aircrafts basically they follow the heat signature. So a nozzle should be producing a less amount of IR radiation so that you can have the stealth capability. Okay, and provide necessary vector thrust. Vector thrust is, for example, your fighter aircraft and all, if you are going with the conventional aileron flaps or for the maneuvering of your aircraft, it will take more time. So instead of that, by changing the direction of your thrust, okay, you can maneuver your aircraft effectively, that is fighter aircrafts. Okay, so that changing the thrust direction, what we call it as the thrust vectoring. So your nozzle also should be capable of producing the thrust vectoring. Okay, and obviously at the end, any aerospace applications, you should have a least amount of weight and cost as well as maintenance. Okay, so these are all the basic requirement of your exhaust nozzle. So next we are going to see first what is this variable area nozzle and what is the need for this variable area nozzle. Okay, so variable area nozzle means, as your name suggests that in a nozzle which is capable of varying its area ratio. That is, you can change the A by A star. Okay, so A by A star, that is why we have to change this, because we have seen any nozzle which is designed for a fixed area ratio, it is capable of producing only one Mach number and capable of expanding only one flow to the correctly expanded case. So if I want to operate my nozzle always correctly expanded case, means what I have to do is that I have to change my area ratio so that I can change my Mach number. So if I change my Mach number, I can make my nozzle to always operate under correctly expanded case. Okay, and one more, this is the first requirement why we need to have a variable area nozzle is that in order to operate your nozzle always at the correctly expanded case so that you can have the maximum thrust generation. That is the first requirement of your variable area nozzle. And second is that, for example, what are the other applications where we are going to use the nozzle? For example, we have a supersonic wind tunnel or hypersonic wind tunnels. Okay, so a supersonic wind tunnel, the cost of making one supersonic wind tunnel is very, very costly. Okay, so in a supersonic wind tunnel, you will have the convergent divergent nozzle to produce the required supersonic flow. If you are having a fixed area ratio, meaning is that you should have a multiple number of supersonic tunnels to generate or to test the different Mach numbers, right? So because it's not like your flow condition will always only one Mach number. You will have a different operating condition, meaning is that you have to test your object under different Mach number, supersonic Mach number. So to generate different supersonic Mach number, obviously you need to have a variable area nozzle. So that you can reduce the cost. Or else what? We have to have a multiple number of wind tunnels. And if you are having a fixed area ratio, means you will have only one Mach number generation. So instead of that, if I'm having a variable area nozzle, I can generate in the same tunnel, I can generate the different Mach number. That is the second need of your variable area nozzle. And third one is that in a fighter aircrafts, it should be always fitted with the variable area nozzle. Why a fighter aircraft should be fitted with the variable area nozzle is that we already know all the fighter aircrafts are fitted with the afterburner. Why do we need afterburner in a fighter aircraft? You know that during your subsonic operations, as your Mach number increases, your drag will be increasing. When it is reaching your sonic zone, that is transonic flight, what happens? You know that your drag generated is increasing rapidly, almost 10 to 20 times. That is during your m is equal to 1. What happens is that your drag is increasing to very high value. Okay, so if the drag is very high value, means what does that mean? The forces acting on your aircraft, if the 10 times increase in drag means obviously there is a 10 times increase in your force acting on it. Okay, so in order to overcome that, because of this 10 times increase in the load, what will happen? Your aircraft structure will fail. In order to overcome that, what we have to do is that we have to escape from our subsonic to supersonic in as much as shorter time possible, so that we won't have too much stress on our aircraft structures. Okay, so for that, what we do is that we always have an afterburner. Okay, afterburner, right? We have already studied this in the first chapter. So in the afterburner, that is after your flow comes out of your turbine, you can further once again do the combustion and increase the, that the thrust generated depends on your exit velocity. Your exit velocity is function of your flow temperature T0. As long as I increase my T0, I can increase the exit velocity. Okay, so you can ask, why can't we increase the temperature, the same temperature in the combustion chamber itself? It is because we have turbo machinery. After your combustion chamber, we have the turbine. So with this turbine is limiting how much temperature I can increase in my combustion chamber. But once your flow comes out of your turbine, after that you are having a nozzle only. So there you can increase your temperature momentarily and to increase your thrust to very high value so that I can accelerate my aircraft from subsonic to supersonic in a shorter span of time. Okay, so now that is how come it is. So that means all the fighter aircraft will be fitted with the afterburner. Now comes the question: why does this afterburner needs a variable area nozzle? That is our question, right? So the mass flow rate passing through your nozzle, basically it is function of your throat area, Mach number, and your throat area, P naught, and divide by root of T naught. The mass flow rate passing through your nozzle is basically proportional to what is the area of your throat. Higher the throat area, you can have the higher mass flow rate. And as long as you increase your P naught, you can increase your mass flow rate. Or by decreasing the T naught, you can increase your mass flow rate. Or what does that mean? If I'm going to increase my T naught, the mass flow rate is going to be decreased. So what we are doing in the afterburner? In the afterburner, we are increasing the temperature. Okay, when I increase the temperature, there is no change in your P naught actually. Okay, your P naught is fixed, but I'm increasing my T naught. So what will happen? Your mass flow rate choking will occur yearly, which is going to limit how much amount of mass flow rate passing through your nozzle. So we have a thrust m dot A into 1 plus F into UE minus UA, let's say it is correctly operating condition. So what happens if I'm going to increase my T naught? The mass flow rate is getting decreased. Even though you are increasing your exit velocity, your mass flow rate is getting decreased. So what will happen? The increase of thrust due to increase in velocity may be compensated or reduced due to decrease in the mass flow rate. So in order to avoid this, what we do is that we will have a variable area nozzle. So I will increase my throat area. So if I increase my throat area means what will happen? Whatever the mass flow rate reduced due to increase in T naught will be compensated by this increase in area, so that I can have a same mass flow rate with increased velocity. You won't have much of increased mass flow rate. You can have a reduced mass flow rate, but you can't increase. Only increase will be how much amount of fuel you are burning. Okay. So when I increase the area, what will happen is that whatever the whatever the limitation caused by your increase in T naught will be removed by this increase in increase in A star, so that you can have the increased thrust during your afterburner operation. That is why whenever we are having an afterburner, okay, to compensate for that reduction in the mass flow rate, we will be always having a variable area nozzle. In the variable area nozzle, we will increase the throat area. By increasing the throat area, I can increase the mass flow rate. So these are all the three basic requirement of an why do we need a variable area nozzle? First one is to operate your nozzle at always correctly operated condition. Next one is to generate multiple Mach number in a same internal, and third one is to accommodate your afterburner operation. We need this variable area nozzle. Okay. So now we are going to see how do we achieve this variable area nozzle, or how do we have produce this variable nozzle. We have three types of variable area nozzle. One is central plug type, another one is the ejector type, another one is the iris type nozzle. Okay. So what is the central plug type is that you will have a kind of spike-like arrangement at the exit of your nozzle. Okay. So what we will do is that by adjusting the location of the central plug, either by moving in the forward direction or in the backward direction, I can vary the throat area. Okay, so obviously by either I can vary the throat area, I can vary the exit area. So either such two ways. If you want to change the mass flow rate, you have to change your throat area. But if you want to get a correctly expanded case, means you have to either change the throat area or you have to either change the exit area. So by this central plug nozzle, we can vary the area ratio. Okay. The second one is the ejector type nozzle. So basically ejector type nozzle means that you will have the movable flaps. Okay, by this movable flap you can operate your nozzle, you can make them as a conversion nozzle during a subsonic operation. The same nozzle can be made into conversion diversion nozzle. As long as you adjust your flap, you can change it. Okay, so this flap mechanism, let's say if you want a super subsonic flow, you will make your flap arrangement will be like this. If I increase this flap, what will happen? This same nozzle will become conversion diversion nozzle. So based on your back pressure and your inlet pressure, so that you can adjust your eddy ratio so that you can operate your nozzle at always correctly expanded case. Last one is nothing but an iris nozzle. Basically, iris nozzle is similar to your flower petal. Okay, so it is capable of varying the throat as well as varying the exit area. Okay, so it's kind of like a flower petal. This iris nozzle basically it's look like a flower petal. So you can either increase the throat area or you can vary the. You can make the same nozzle into conversion nozzle, conversion diversion nozzle. You can increase the throat area or you can simply increase the diversion, that is exit area. So by making this arrangement, you can have the variable area nozzle. So these are all the basic three types of mechanism we used to get the variable area nozzles. Okay, so next section we are going to see is about the thrust reversal. Okay, so what is this thrust reversal, or why do we need the thrust reversal? Is that, you see, for example, there are situations where you have a limited runway length. For example, during your in Navy and all, your length of your runway is very, very small. Okay, so when your aircraft is landing, you might have seen in the commercial aircraft, the spoilers at the top of your wing, there is a plate-like mechanism. It will come out. So by making it come out, what happens is that you will increase the drag. So by increasing the drag, you can reduce the velocity of your, because when it is landing, it will, after landing, it will have a high momentum. So you have to reduce this high momentum as much possible so that you can have the lesser amount of runway length. Okay, so one way is to use the these spoilers, which will increase the thrust, or another way is to introduce the brakes, but brakes also will limit, okay, how much speed you can reduce. Okay, in two-wheeler itself, if you are applying our brake at 100 km/h, what happens? Your brake sometimes fails, right? But you can just think in your aircraft how much velocity is landing. After landing, what is the other mechanism we can use to reduce our momentum of our aircraft is that's what thrust reversal. Okay, in reversal means we will produce the thrust in the opposite direction so that it will become, so basically we are producing the thrust to overcome the drag. But in the thrust reversal case, what we'll do is that we will produce the thrust in the drag direction itself so that I can decelerate my aircraft in a shorter runway distance. So you can have a limited amount of your runway length. Okay. So how do we achieve the thrust reversal? Okay, in case of your propeller driven aircraft and all, we can, by changing the pitch of our propeller, we can change the direction of your thrust produced. So as long as I change the pitch, what happens is that instead of thrust producing in the forward direction, it will be produced in the opposite direction. So that is going to decelerate. In the propeller driven aircraft, thrust mechanism is very, very simple. As long as you change the pitch, you can change the direction of your thrust. But it is not simple in case of your jet aircraft. Okay. What we will do is that in case of your jet aircraft, we will direct the jet direction. So that is, we will produce the jet in the opposite direction so that you can have the reverse thrust. Okay. So first type of thrust reversing mechanism we use is something called target type or bucket types. Okay, so what is this target type or bucket type? So initially this bucket is basically it is the enclosure of your engine. Okay, once you land, what will happen by using a pneumatic system or hydraulic operating system? We will make this two whatever initially they are closed. Okay, now what happens is that when we operate it, they will come and close or block the flow comes out of your nozzle. So that means what will happen? Initially your thrust is moving like this. When I put this bucket, what will happen? Your thrust will be produced in the reverse direction. Okay, when it is producing the reverse direction, what will happen? The momentum of your aircraft will be reduced drastically. Okay, this is what we call it as the target type thrust reversal mechanism. We will produce a thrust in the opposite direction. Next one is something called clamshell type. Okay, so basically this clamshell type we use in the turbofan engines. You know, in the turbofan engine, we'll have a cold flow and hot flow. Okay, so what we do is that in this clamshell type, we will have the bypass, that is cold flow section, right? We will block the cold flow. By blocking the cold flow, what we will do is that the flow will come out in the same as that of your kind of your bucket type. The only thing is that in bucket type, we directly control the main jet flow, that is hot gas, whereas in the clamshell type, we control the cold flow in the opposite direction. We divert our cold flow in the opposite direction. By diverting it, we are able to produce the reverse thrust. That way, we can decelerate our aircraft rapidly. Okay. So with this, I'll end this lecture. So what are the things we have seen in this lecture is that we started off with what is the basic requirement of our exhaust nozzle and what is the need for our variable area nozzle and how do we achieve the variable area nozzle. We have seen three types, plug nozzle, another one is the ejector type, another one is the iris nozzle, and then we have seen what is the need for a thrust reversal and how do we achieve the thrust reversal in the jet engine aircraft as well as in the propeller aircraft. In the propeller aircraft, we change the pitch of our aircraft to change the direction, whereas in the jet engines, we block the flow going out of your nozzle or in the bypass section and make them flow in the opposite direction. By making them flow in the opposite direction, we are producing the reverse thrust.
Like, share and subscribe. Hit the bell icon for more updates.